Welcome friends to EPG Pathshala and special welcome in the paper of numerical methods under the subject of information technology. Today we are going to learn in the second module the different types and sources of errors. That is our module entitled, and in our previous module we learned about numerical methods, why do we need them, what are their importance, and today we are going to learn about a significant digits, different types of errors, sources of errors, and what is meant by stability of a problem and sensitivity of a problem. Our main focus would be on how to evaluate, how to estimate and have a idea about different type of errors which occur under numerical computations. So, first let us take significant digit. What is meant by significant digit? See, all non-zero digits are always significant, but when 0 is there, it may be significant or may not be significant. See, the importance of significant digit arises especially when the number is between 0 and 1, because at that time, see, we are interested if you have a constant, let us say of the order of 10 raised to minus 6. So, it has 0.00005 leading zeros and then the non-zero digits start. And if you are interested in first 5 non-zero numbers, then we need the answer correct to 5 significant digits. The answer correct to 5 decimal places will be all zeros. So, that is why the role of significant digit comes in. So, let us just learn the rules one by one. See, when a digit is said to be a significant digit. See, the first rule is every non-zero digit is significant. So, if a number does not have a 0, all the digits are significant. So, like for example, here 9.5763, all the digits are significant, it has 5 significant digits. Similarly, 492, it has 3 significant digits. Any 0 occurring between non-zero digits is significant. So, like for example, 2047, so all the digits occurring in this number are significant. Similarly, 50.032, all both the zeros occur, see they are occurring between non-zero digits, so they are significant. See, every non-zero digit is significant, we have to keep in mind. So, 0 may be significant or may not be significant, that is a question. So, we need to find out if a number has some zeros in it, we need to find out when is this 0 a significant digit and when is this 0 not a significant digit. So, what we have learned is so far that a 0 between non-zero digits is a significant digit. The third rule, and that is leading zeros, that is the zeros occurring before non-zero digits are not significant. So, like for example, if we have a number 0.0123, so both the occurrences of 0 are non-significant. So, here 0.0123 has only 3 significant digits, namely 1, 2 and 3, and similarly 0.00000000123 also has only 3 significant digits, 1, 2 and 3. And finally, the trailing zeros, that is zeros behind the number, behind non-zero digits are sometimes significant and sometimes may not be significant. If they are occurring after decimal sign, they are significant, like if it is 3.000, so they are significant, because that means that up to those 3 decimal places the numbers are zeros. But many times, like we talk about that, okay, what is the salary? 40,000 K, you may say 40 K. Or sometimes when you ask, someone asks you that what is the time series going on, one may say, okay, in thousands. So, there you may say 4, 5, and so that time 4,000 or 5,000, instead of that we say 4 and 5. So, in that kind those trailing zeros become non-significant. Let us take one illustration. Just suppose 6.4320. So, here all the 5 digits become significant, because 0 is occurring after a non-zero digit after the decimal sign. In 0.0643, both the occurrence of 0 are non-significant, only 6432 are the significant digits. 64 has 2 significant digits, 64.0 has 3 significant digits, 6.432 into 10 raised to 4 has 4 significant digits, 6432, and 6.43200 when we are saying, then it has all the 6 digits are significant digits, and 2000 it depends upon where it is occurring, what does it stand for. So, I am just saying right now it has one significant digit, namely 2. So, with this, now let us come to, just to get the feel of significant digits, now let us today come to what are the different sources of error. See, sources of error, due to those sources the errors occur, and due to these errors we need to understand what are those type of errors. As a sources are the cause and the types of error are the effect of those causes, and we need to understand the different types of errors which occur under numerical computation. So, coming to different sources of errors, see, the first source of error comes what we call as mathematical modeling error. See, when in the physical sciences or engineering problems or in business houses, one comes across a problem, a mathematical model is built upon it. While building mathematical model, conservation of different issues is kept in mind, but at the same time certain aspects may be ignored to make the model less complex. Certain variables which are felt not to contribute significantly may have been eliminated, and as a result the model built cannot be thought as a pure true reflection of the actual physical phenomena. It is a to little or some more extent a compromise on the physical phenomena. It does not reflect purely the physical phenomena. So, certain approximations are made during the building of the mathematical model, certain variables eliminated, certain procedures not considered. Just for example, if we take example of a body falling from the atmosphere, maybe ordinary ball falling, we may ignore the friction of the air, and the model, the equation which we frame on it of a example of a ball falling under the ground, we may not consider friction of the air. But at the same time, if we are considering a physical phenomena of spaceship entering the earth's atmosphere, then the air friction is to be considered is a must. So, depending upon the problem, certain variables may have been eliminated, certain compromise may have been made, and that does introduce error to some extent. So, the errors which are built in the mathematical model, which are due to building of the mathematical model of the actual phenomena, those errors are known as modeling errors. The next type of error is, now once the mathematical model is built, the readings are to be taken, parameters are to be estimated, and for that different measuring equipments, measuring machines or measuring devices are used, and the data is taken. There are limitations of these measuring devices, like for example, if I am measuring a diameter of a wire by inch tape, its least count is only 1 centimeter, 1 millimeter, it can't measure less than that. I will need more sophisticated equipment for that, maybe vernier calipers or maybe screw guys. So, depending upon the limitation of the equipment, the sensitivity of the equipment being used, and also the measuring methods may use, there would be some errors in measuring because of the least count of the equipment and because of the method being employed. And so, these what they are called are the measurement errors. Maybe if you want to measure the result in an experiment, some readings are to be taken of the temperature at 3 o'clock, but somehow just you got an emergency call, the reading was taken at 3.5, then that is also leads to a measuring error. So, different measurement errors also occur. The third error, which are known as human errors, many people call it blunders. The error due to humans, due to oversight due to non being serious about it. Maybe some data is measured and then it is being typed, maybe the operator read instead of 3 read 8 or some other, because ultimately humans are involved, to err is human. So, there may be some different type of errors because of human involvement in the data, and they are called human errors or may be called blunders. So, when a problem comes to numerical analyst, all these 3 errors are combined when the maybe equation is framed or data is given, maybe in the form of a matrix, maybe in the form of an equation to be solved, maybe in the form of a differential equation to be solved, maybe derivative or whatever it is, it already has errors in it, and those errors are called inherent errors, because a numerical analyst, a person who applies numerical methods to solve the problem, already inherits the error, cannot do anything about it, because does not know what the errors are. But these 3 procedures, these 3 sources of errors contribute to the problem, the errors, and these errors come under the inherent errors. Whatever best the numerical analyst can do about is examine the problem, data problem. If the problem is stable, no issues. See, a stable problem means, that is, if there is slight change in the data involved, slight change in the coefficients, there will not be much drift in the result. Like example of numerical integration, it is area under the curve. The function values are given at certain points. So, if there is a slight change in the function values, still the area also there would be slight change. So, that is a very stable problem. But in case of numerical differentiation, because differentiation means direction of the tangent. So, if there is a slight drift in the function value, shape of the curve may change to be fitted. As a result, the direction of tangent will change. So, if the data is such, the points are such that slight change in the values makes the tangent change, so that times the problem is unstable or it is sensitive. Like again, if you are finding roots of an equation, the coefficients may be such that slight change in the values of the coefficient changes the roots to a great extent. In that case also the problem is sensitive. So, all the best the numerical analyst can do is examine the problem. If it looks to be sensitive problem, meaning by change in the coefficient changes the results to a great, slight change in the coefficients makes the result drift to a great extent, in that case he should advise the people that just doubly check your data, that there are least error involved in your data. Otherwise, the person, the numerical analyst, goes ahead with the problem and solves it. So, for us under numerical methods, we are more concerned once the problem is come and we are applying the methods to solve the problem, what different type of errors can come in. So, when we apply the numerical methods, one is we apply the method on the computers. So, computer arithmetic comes into picture. See, the numbers have finite precision, and due to that addition, all the computer operations give a rise to surd error, which are known as round off errors. And secondly, see, because we are applying numerical methods, they are approximate methods. See, these methods convert infinite process to a finite process, and as a result the error due to the methods, due to the approximation methods, and those methods are called truncation error. And these truncation error and round off error total, they give us the total numerical error, that is the error caused, error arise due to numerical computations. Now, with this let us come to one by one. See, we are concerned with two errors, truncation error and round off error. Rest of the errors, when problem has already come, we can't help it. All we can do is best is advise the people who brought their problem to us. So, first let us focus on truncation error. See, as the name is, truncation error arises due to truncating an infinite process, theoretically infinite process, to a finite process. Because though the theoretically it says that you will achieve the exact result if you do this an infinite number of times, but we cannot continue the method infinite number of times, we have to terminate the process after finite number of steps. And so, due to truncating the infinite process to finite number of steps, the error which comes in is called truncation error. The most common example is given by the people is the truncating an infinite series if we are finding to finite number of terms. Let us take this example first. A simplest example possible is e raised to x. We know the series of e raised to x is given by 1 plus x by 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. And this series is convergent, it is called Maclaurin series, a special case of Taylor series, and this series is convergent for each and every value of x. What does that mean is that as you proceed, as the number of terms increase, the right side sum goes nearer and nearer to e raised to x. The smaller the x, faster will be the convergence. Now, for illustration, let us say we evaluate the right hand series to get a value of e raised to x certain point. For simplicity, let us take the point, but let us say we just take first 4 terms to evaluate e raised to x. So, e raised to x we are taking as 1 plus x square by 2 factorial plus x cube by 3 factorial, and x raised to 4 power terms and higher terms we ignore. So, what is going to be the truncation error? The whole series minus the terms which we have taken. So, it is going to be x raised to 4 by 4 factorial plus x raised to 5 by 5 factorial plus so on. Let us take this example. Suppose we estimate e raised to 0.5 using different number of terms, and we know the value of e raised to get a number of good number of decimal places. So, let us use it. Exact value of e raised to 0.5 is 1.64872 up to 5 decimal places, and let us use the series terms to calculate the value of e raised to x one by one. So, the first column gives us the number of terms. Say suppose just we are taking only first term, that is only 1. So, we are approximating e raised to 0.5 by just 1, and actual value is 1.64872. So, the last column gives us the absolute error 1.64872 minus 1. So, absolute error is 0.64872. Suppose we take 2 terms. So, 1 plus x. So, our value estimate of e raised to 0.5 will be 1 plus value of x is 0.5. So, 1 plus 0.5. So, answer is 1.5, and absolute approximate error is current value minus previous value and absolute value of that. So, 1.5 minus 1. So, it is absolute value of 0.5, and relative approximate error would be that is absolute approximate error divided by the current estimate. So, 0.5 by 1.5 into 100. So, it gives that the relative percentage of approximate error is 33%, and actual absolute error you subtract the value obtained from 1.64872, it gives you 0.14872. So, the error has decreased. Again, if we take the number of terms as 3, so it is 1 plus x square by 2. So, 1.5 is 1 plus x, let us add in that 0.5 square by 2. So, we add so we get the answer 1.625 0.25 by 2. So, 0.125 is added, we get 1.625, error absolute is now 0.125. Similarly, take the ratio of 0.125 to 1.625 gives us the relative approximate error has decreased now to 7.69%, and the absolute error has decreased to 0.02372. One more term, and you see that the relative approximate error has decreased to 1.27% and absolute error has decreased to 0.00289. And finally, if we have 5 terms, means we are going up to x raised to 4 by 4 factorial, and fifth and higher powers are being ignored, not considered. In that case, the sum is 1.64843617, and so it is correct up to 3 decimal places. The absolute error is only 0.00028 and relative percent of approximate error is 0.16%. See, what we learn from this is, as the number of terms are increasing, that is, then the absolute error is decreasing. See, this is Taylor series is a very important series which is a backbone of many numerical methods. The expression of Taylor series, you know it very well. About any point A, if function is differentiable, then you can go to any number of terms. It is an infinite series. So, f x is given by the value of f at the point x can be obtained in terms of the values of and powers of x minus a, where if you know the values of function at derivatives at the point a, one can use it. So, f x is f a plus x minus a into f dash a plus x minus a square, a second derivative by 2 factorial and so on, and this is an infinite series. And if the series converges, we can use up to certain number of terms, and if we want to stop at after nth term, see, so you have the, you are approximating f x by the sum sigma k equal to 0 to n f k a by k factorial x minus a raised to k. The e raised to x series which we consider is a special case of this series when our a was 0 and derivative of f x is e raised to x only, and plus we get the remainder term. This remainder term is the truncation error term, where this has been evaluated in the case of Taylor series, which comes out to be n plus 1th derivative at some point xi, and xi is a point between a and x, but what the value is not known to us, upon n plus 1 factorial into x minus a raised to n plus 1. So, the nearer x to the point a, x minus a will be smaller, and x minus a raised to, if should be less than 1. So, x minus a raised to n plus 1 will be quite small. Now, let us take the second example of numerical integration, and let us consider the truncation error under numerical integration. What we know is that numerical integration, in the case of numerical integration, the a to b f x dx is given by area under the curve. See, it is x equal to a. So, basically under numerical integration we have to determine the area. If I am finding a to b f x dx, I have to determine area of the strip under the curve from x equal to a to x equal to b. Theoretically, see, it is the notation is a to b f x dx. Theoretically, the integration, this is the graphical interpretation, is area under the curve. Theoretically, how do we find? So, it is integral sign stands for the summation. Dx means delta x, small delta x. So, f x multiplied by delta x small, where delta x tends to 0, and summation from x equal to a to x equal to b. So, it is integral is defined as limit delta x tends to 0, f x into delta x gives you the areas of the rectangles under the curve, small is rectangles of the very small size, and that strips we frame under the curve of the width of the strip is tending to 0, as small as possible, and we add the areas. F x into delta x is the area of those strips, and we add the areas of those strips under the limiting sense as delta x tends to 0 is the value of the integral of the function. Now, if you want to apply this technique, we cannot do with the infinite small strips, we cannot make delta x tends to 0. All we can do is we take finite width rectangles and sum it, and due to taking finite width of rectangle, the error which will come in will be a truncation error in this example. As such, the number of rectangles should be infinite, but we cannot take infinite small width, we have to take finite width rectangles. So, we have converted the infinite process in the infinite number of rectangles to finite number of rectangles, and due to this conversion, the error which will come in would be an example of the truncation error in the evaluation of numerical integration. For illustration, let us take the example. Again, we have taken a very simple example, so that the ideas become clear. So, let us take the function f x equal to x square, and we are integrating it from 2 to 4. Integral of x square is x cube by 3, we know it, and 2 to 4. So, 4 cube minus 2 cube by 3. So, 64 minus 8 by 3, the answer is 18.67, it is 18.6666, so on. So, 18.67 is the answer correct to 2 decimal places. We know the exact answer here. Now, let us apply the numerical method here. For simplicity, just for ease and convenience, let us just consider 2 rectangles of width 1 each. We are integrating 2 to 4. So, we are taking 2 rectangles, 2 to 3 one rectangle and 3 to 4 another rectangle, and the area we find. So, the area, shaded area of these rectangles is our estimate for the integral, and whatever area is unleft to be covered shown by the red dots, that amounts to the truncation error in this example. So, if you go to the calculation, see the estimated value of the integral will be width is 1. So, f x is 1, the width is 1 and height is first rectangle of height 2. So, 2 square, function is x square. So, f x is 4. So, 1 into 4 plus second is again 1 into 3 square, that is 9, 9 plus 4 13. So, estimated value of the integral is going to be 13. And what is the truncation error? Truncation here is 18.67 minus 13. So, the truncation error value is 5.67. Let us reduce the size of the rectangle, increase the step size, increase the number of rectangles, because in actual our number of rectangles should tend to infinity, width of the rectangle should tend to 0. So, let us reduce the width of the rectangle, instead of 2 rectangles, let us take 4 rectangles. So, each of width 0.5 now, and again do the job. So, this time the height of the rectangles will be 2 square, 2.5 square, 3 square, 3.5 square. So, function values are 4, 6.25, 9, 12.25, and so the area will be, width is half now. So, half into 4, half into 6.25, half into 9, half into 12.25, and so estimated integral gives the value 15.75. So, the truncation error is 18.67 minus 15.75. So, it is 2.92. It has reduced, it has almost become half of the previous case, from 5.67 the error has reduced to 2.96. So, if you look at this graph, see now 4 rectangles of width 0.5, and you can see the truncation error area has decreased each, and the rectangles now 4. So, now we can again continue this process. We may make 8 sub rectangles and again do the same. Now, the height is 2, 2.25 square, 2.5 square, and so on up to 3.75 square, and this time the area comes out to be 17.1875. So, truncation error has further reduced to 1.4792. See, what we have learned from both the previous examples is increasing the number of steps, reducing the step size, the step is here width of the rectangle. So, increasing the number of steps and reducing the step size reduces the truncation error. Our job is, we would like to reduce the numerical error. So, truncation error can be reduced by increasing the number of steps and reducing the step size. Similarly, if you take the example of a root of an equation f x equal to 0, we would be learning many methods for it. The first and simplest method which we learn is bisection method, and if the root lies between the interval a and b, then in the case of bisection method we know that the error, the truncation error is always less than equal to absolute value of b minus a by 2 raised to k, where k is the iteration number which is being performed, and this will tend to 0 as k tends to infinity. If k tends to infinity, 2 raised to k becomes large and large, and b minus a by 2 raised to k tends to 0. So, again here the same scenario, if we continue up to infinity, the truncation error will be 0, but we have to stop after finite number of steps, and in that case our error will be less than equal to b minus a absolute value by 2 raised to k. So, as we increase k, as we increase the iteration, as we increase the number of steps, our truncation error will go down. Last example for truncation error, let us take the case of numerical differentiation. What is the derivative of a function? Derivative of a function at the point a, f dash a, is given by limit s tends to 0, f of x plus h minus f of x by h. So, here again we are taking the difference of the function value at x plus h and f x, but now this argument h has to be as small as possible. Under limit s tends to 0, it gives us the derivative. In case again we take the simple example of f x as x cube. So, f dash x we know is 3 x square. So, at the point 2, if we know, the value of derivative is 3 into 4 into 12. Now, let us, because we cannot take limit as s tends to 0, but we can take h small. So, we take h finite value. If I take h to be 0.1 and try to find derivative of f at 2 using the formula f at 2.1 minus f of 2 by 0.1, h is 0.1, x is 2 here. So, f dash 2 estimate is 2.1 cube, because f x is x cube here, minus 2 cube upon 0.1, and the answer is 1.261 upon 0.1. So, 12.61. Actual value is 12. So, our absolute error is 0.61 and relative error is 0.61 by 12, because correct value we know is by 12 into 100. So, error is 5.08%. See, if you look at the graph, it tells us, so you the derivative as such is the tangent, but we are estimating the derivative at the point x 0 by taking the next point x 1 as x 0 plus h, which we have shown by x 0 plus delta x. Value we are taking a straight line, we are estimating at y at x plus x 1 as x y at x 0 plus delta x, and the difference, because usually we do not know the function, here we know the function. So, we estimate by straight line and we take the difference and the ratio, and this is how we get the estimate for the derivative. Again I reduce the step size h, instead of 0.1 I make it 0.05. So, if I reduce it to be 0.05, then the estimate is f dash 2 is numerator is difference of f at 2.05 minus f 2 upon 0.05, and so the answer is 12.3025 in this case. So, the absolute error is 0.3025 and relative absolute error becomes 2.52%. The purpose of doing all this exercise is that to understand first that the truncation error is due to truncating an infinite process to a finite process. It is due to the numerical method being applied, because in the method we cannot go up to infinity. It is due to terminating the process after finite number of steps, and secondly, if we increase the number of step sizes and reduce the size of the step, then the truncation error will decrease. That is very obvious. If we reduce the step size, the number of steps to be performed will increase. So, the truncation error. So, if we wish to reduce truncation error, we have to reduce the step size and increase the number of steps. Now, let us focus on second aspect of today's our module talk, and that is the round off error. What are round off errors? For that, just let us glance at the way the number are represented. First thing to be noted is, see, in our decimal number system, so we human beings have 10 fingers, and that is how the decimal number involved using 10 digits 0 to 9. Computers work on only binary, their computers are binary valued system. You may call it is a 2-finger animal. It has only 2 states 0 and 1, like on or off, and there every number is represented using a binary number system. I understand you are very well versed from the other subjects how to convert a decimal number to a binary number and how to convert a binary number to a decimal number. See, in case of our decimal number system also, like 2 is represented as a finite precision, 10 is represented, but there are some numbers like √2 which goes up to infinity, it cannot be written using finite precision. Same way 1/3, 0.333 it goes on. Our E number is 2.7182 where it goes on. So, they are not represented by finite precision. But second point to be noted is, even if a number has a finite precision in a one particular number system, it need not have a finite precision in another number system. Like for example, 1.1 in a decimal system it is 1.1, but if you represent the same 1.1 using base 2 in the binary number system, it goes on 1.0001100110011000, it goes on like this, 1100 recurring, and it does not terminate. Due to this, what happens is computers have finite storage for a number, finite bits reserved for a particular number. A number not terminating after finite number of storage places cannot be represented exactly in a number system, in a computer. So, let us take suppose a floating point is there, suppose the number is 5, just for illustration purpose. Let us say we are only having 5 boxes. So, the number is suppose 562 and one box for decimal system fixed. So, number is 5, decimal storage box is fixed. So, 562.36, this is how it will go. Now, suppose I have only place for 5 digits, one for decimal, and let us say the number is 458.9875. It has 2 extra digits, they will be lost while storing, they cannot be stored. There are 2 ways of doing it, either just chop off the extra digit. So, 75 to be chopped off, that is called chopping, and other is round. Whenever you are chopping off, before that round the last digit to the best place. So, like we 458.98 will round it to 458.99, it is called rounding, and the error due to rounding is 458.99 minus 458.9875, that is 0.0025, that is the rounding error due to rounding, and this relative percentage is 0.000545%. So, due to computer arithmetic, the rounding of errors occur. Similarly, let us take another number 5.995, and if we represent this as due to rounding and the number is 5.9875, error, absolute error will be 0.0025 and relative error is 0.041754%. The point to be noted here is number was small, absolute error was small, but the relative error has increased to a great extent. And for that, the representation, the floating normalized floating point representation method is there to represent a number. For illustration purpose, if I am using a decimal system, we will have, see, like 562 point, decimal is reserved, place is reserved. So, it is like 562.36 will be represented as 5.6236 into 10 square. The last 2 orange colored, that is for the exponent of 10. So, every number will be represented as digit, sign, digit, then the digits after decimal place, which is called fraction or mantissa, and the last digit will represent the power of the 10. In this way, the large numbers also can be represented easily. You can represent a bigger range, number 1, and you will find if you do the calculations, then though the absolute error in the large numbers will be large, but the relative errors when you use normalized floating point representation is of the same order. So, that is one great advantage. See, when you represent numbers using floating point representation. So, in the case of normalization, it looks like for base 10, it would be of this form, plus minus, one box for digit, one box for sign, then there will be only one digit D, point, and then you have mantissa, and then that is point F1, F2, F3, F4, and into you have the number is 10 raised to power. So, number will be represented as D, F1, F2, F3, F4 and the exponent E. For our IEEE 754 floating point standards, for 32 bits are 1 bit S sign, then you have 8 digits for sign, 8 bits for exponent, and then 23 bits for representing the fraction. And for 64 bit representation, you have 1 bit for sign, 11 bit for exponent and 52 bits for fraction. So, what we have seen is that when we represent a number in computers, due to the finite representation, the error has to come in, and that error is rounding off error. Now, when we add two numbers, they already have round off errors. When we do any arithmetic computation, addition, subtraction, multiplication, then these rounding off errors get compounded. So, error propagates. So, those who are interested in going in details about this error propagation, you please refer Don and Maclaurin book, which I have mentioned in the additional reading material. I have just listed two formulas here, like in addition, the error in A plus B gets added up, error in A plus error in B, and plus new rounding of error will occur. When there you are adding, rounding of errors are getting compounded and one new rounding of error will occur. So, the error will increase. Same way in the case of multiplication, I have mentioned relative error in A into B is relative error into A plus relative error in B and plus again rounding of error due to multiplication. Similarly, for subtraction, and subtraction of is more could be more serious many times. So, rounding of error increase with the increase in computations, and the higher the number of steps, more shall be the rounding error. See, here there is a contradiction now. Rounding of error will increase with the increase in number of steps. So, if you increase the number of steps, more number of operations, more number of computations, rounding of error will increase, truncation error will decrease. If you reduce the number of steps, rounding of error will be less, but the truncation error will increase. So, depending upon the problem, one has to strike a balance between truncation error and rounding of error, because they move in different directions. Sometimes it does, you may find in real life situation when you are performing iterations, your method is converging and all of a sudden the values may start diverting, and that happens when the rounding of errors start playing more dominant role instead of truncation error. So, one should be aware about this and try to balance. Like, see, this is an example, if you are having only 2 fraction digits 3.57 into 2.13, for only if you are retaining 2 digits you will get the answer 7.6 due to rounding error, whereas the actual value is 7.653342. So, the total numerical error in the problem is truncation error plus round of error. To reduce the round of error, less number of steps you do it, or you increase the number of significant digits. That is, if you are having this problem, instead of single precision use the double precision numbers, instead of 32 bit use 64 bit numbers, and you have to be careful if you are having subtract, that is cancellation. The second thing is, see, in case of addition, because of this floating point, normalized floating point representation, if you are having a numbers which are diversified in their ranges, then there is a special technique to reduce the round of error. Let us say, for example, if you are adding certain number of numbers and they are in different ranges, it is always advisable to arrange them in the ascending order and then add them one after the other in that sequence to reduce the round of error to the maximum. So, a detailed discussion you can have about this rounding error propagation in the Don and Maclaurin book and other literature, which is mentioned in the additional reading material. So, the truncation error can be reduced by reducing the step size by increasing the number of steps. So, this is how the numerical errors occur. They have to be controlled. There may not be any systematic and general guidelines or approaches to control the numerical error. It depends upon the data, it depends how they are playing the role with the particular problem, and one should have idea that how these errors occur, and especially one should be very careful if subtraction of 2 similar small number is occurring, that at that time and division is there, at that time the rounding of error will become very large. And so, this is how we have to. And secondly, if one needs to check whether the system is unstable or one is sensitive, because in that time a slight change in your calculations, a slight error will lead the result to diversify the result to a great extent. So, these are the things to be kept in mind. So, in our today's module, what we have learned is majorly that what are the different types of error and what are the different sources of error. Sources of course are modeling errors, the human error and measurement error, nothing can be done about them, and when they come to numerical analysis, the errors to be controlled in the hand of numerical analysis are the truncation error and round of error. But of course, these two errors are go in two opposite directions. The truncation error is to be decreased by increasing the number of steps and reducing the step size. The truncation error occurs because of taking finiteness, because we cannot do infinite number of steps, we truncate the process to finite number of steps, and that is how the truncation error occurs. And round of error occurs because we cannot represent a number up to infinite places, and because of finite precision the numbers cannot be represented completely, and so when we add, and due to the normalized floating point arithmetic, when we add, subtract, the rounding errors get compounded up and the error propagates. And one has to take a strike a balance between the truncation error and round off error. In the case the round off errors start dominating, one has to be careful and maybe increase the significant digits or increase and be careful about it. So, thank you very once again, and thank you for visiting EPG Pathshala. When we meet next, our next module will be on finding the roots of an equation f x equal to 0, and we will begin with the bisection method to find the roots of an equation f x equal to 0. Thank you.